right, welcome back, everybody. Thanks for coming. Today's it's always a little nervous doing review problems or review lectures like this. I do have a bit of a presentation or a slideshow that I'll go through here, just giving sort of a high-level overview of how I think we should be doing thermodynamic problems. But then I guess you get the opportunity to test me to see if this methodology works, because we'll be doing a problem that I have not seen before. And the problem that we chose was from the family of diesel cycles. But before we get to any of that, the first thing I want to do is remind everyone that we have our exam on August the 14th. So today is the 5th. August 14th is next Friday. So we'll run the exam. We'll start at the same time as we started the midterms, but we'll go half an hour longer because there's one extra question here. I'll run a meeting in Zoom from 5:45 to 7:30, but you can also email me if you have any questions. If you have approved accommodations, obviously those will be honored, so any sort of extended time or anything will be honored. And if you have not already, if you do have a conflict on the 14th in this time frame, please let me know and we'll try to schedule something that works for everyone. So the final exam will look a lot like the midterms. There will still be 10 multiple choice questions, but instead of 2, there will be 3 long answer problems. And, I don't think I'm sharing the secret sauce here when I say that the 3 long answer problems will be cycle analysis problems. So we're done in terms of new material. So today will be the first in a series of 5 course review lectures. So the first review, I'll do a little bit of this high level overview, and then I believe that Jack agreed to give us a diesel cycle problem that I can do here. So something that I haven't seen before. But when we think about what we want to do for next class, I would like someone, first I'm happy to take recommendations for the type of cycle that we do next. But then I'll also need someone to volunteer to find us a problem in a textbook that we can do so that I can, again, have this experience of coming into class, not having seen the problem before, and we can sort of work it all out together. So does anyone have a preference for the cycle that we look at next class? So I think the options here are Rankine regeneration. That's here, right? So something where we're splitting the mass off, where we have a Brayton cycle with all of the different components here. So we've got an intercooler, a regenerator, and we've got reheat in between these 2 turbines. So people sometimes find that hard because there's just so many different cycles or so many different states, right? These turbojet engines can be difficult because you have kinetic energy terms. So they're a little bit different. Then we have these last cycles that we did, which are the vapor compression, refrigeration, or heat pump cycles. They can be a little bit difficult because we maybe fix states in a different way. And, it looks a little bit like a Rankine cycle, but it's not quite. We've got this expansion valve here. So does anyone have a preference for the type of cycle that we look at next class?
We maybe look at the jet engine.
Sure. I think that's a good idea. Like I said, I think that the kinetic energy term definitely makes these a little bit difficult. Plus, we got to remember the backwork ratio is 1. Do you mind trying to find us a problem? I think it was Matt.
Yeah, do you want me to look in a textbook for it?
Sure. If you can find one in a textbook, or even if you can find one online, we could maybe try it.
Okay.
Yeah. Perfect. So we will do jet engines next class. So before we get to doing the diesel cycle problem for today, I just wanted to talk a little bit about how do we go about solving problems in thermodynamics. So I think that, one of the first things that I think I told us at the beginning of the semester was that thermo is a class that people tend to either really like or really dislike. And I can't speak necessarily for the people that dislike it, but I think part of the reason that I liked taking this class was that at some point along the path, I realized that all of these problems are kind of the same problem as long as we have a good methodology for looking at solving these cycle problems. So if you open up your exam, right, or I guess you download your exam these days, you'll ask yourself, or you might ask yourself, like, what am I supposed to do because I feel lost? Right? So if you have a cycle problem, I think the first thing we want to do is be able to define the characterization parameter. So how are we going to see how well the cycle is performing? Then we can do conservation of mass on all elements. Now this could be trivial, particularly if all the processes in your cycle are closed processes, right? Because then conservation of mass is just, yeah, all the mass that was there never left, right? Then we can do the first law on all the elements. If we're trying to figure out if something is possible, we might also be asked to do a second law analysis on elements in the cycle. And then from that, we can get symbolic solutions for pretty much anything that a problem can ask us. And then we'll be at this point where we got to fix all the states, right? So this can be tricky. First, we got to know what the fluid is, right? But we also have to know kind of how do we march through state by states and what are the different sort of equations we're allowed to use. But once we do that, we can put that information from all the states into our equations for things like power or heat rate. And then we can put that information back into our equations for our characterization parameters. We can find something like a thermal efficiency or a coefficient of performance. And then sometimes we'll be asked to compare that to the ideal efficiency or the ideal coefficient of performance. Right? Now, one of the other things that maybe you've picked up on through the class is I don't like memorizing things. I prefer to sort of understand things, right? Or break things down into kind of basic processes that we can go through. In this list, I think it's a good list. I came up with the list, so of course maybe I think it's a good list. But there's kind of 8 things on this list, and that's sometimes too much for me to remember. So I like to think about this as 3 different questions, right? So the first is, how do we characterize the system, right? And there's different elements here, right? So we need to know what the major equations are, right? But then we're going to eventually find those things at the end. The second thing, we need to know if the system is open or closed, because that's going to change the versions of the first law and the second law that we're going to use. And as we've already said, it's going to determine whether or not we even really need to do conservation of mass, because it's sort of a waste of time in a closed system to thinking about how mass gets conserved, because all the mass in the system just stays in the system. And then, in order to fix all the states, we need to know what the fluid is, because there's different rules or different twists for how to fix the states depending on what the fluid is. So I think there's generally, when we're doing cycle problems, there's kind of 3 questions that we need to ask. How do we characterize the system? Are the processes open or closed? And what's the fluid? And I think we can characterize or group all of these cycles based on the answers to these questions. So first, how do we characterize the cycle? Or what are the things that I'm trying to find? Right? And ultimately, this is what's the energy benefit. That's always going to be the numerator in these characterization parameters. And then what's the energy cost? That's always going to be the denominator. So we can group the cycles that we looked at here into heat engines. So these are ones where the energy benefit is work or some kind of power, and the energy cost is heat in, right? So these heat engines, the energy benefit is always work or power, which is sort of the rate of change of work over time, right? So the rate of work being done. But then there's some other cycles. We didn't do Brayton refrigeration, so you can take that off all of these different lists. But then we also have other kinds of cycles that are doing temperature control. So the energy benefit for a refrigeration cycle is the heat transfer we're removing from the cold side, right? Or the heat transfer that goes into the cold side of our cycle, but it's being removed from the cold reservoir. Conversely, a heat pump is adding heat into the hot place, right? Or it's the heat that's rejected from the hot side inside of our cycle. The energy cost for all the heat engines is the same. Typically, we're burning something to get heat, although that's not quite always the case, because in something like a nuclear reactor, we're performing this nuclear reaction to get heat, right? But Rankine cycles, Otto cycles, diesel cycles, Brayton cycles, jet propulsion, the energy cost is always the heat that we're adding. If we're doing temperature control, the energy cost, the thing we need to do to make this thing run, is we have to add in net work. And for both refrigeration and heat pump cycles, the net work is only the work that gets added to the fluid by the compressor, because that valve is not doing anything in terms of work. Our next big question is the system open or closed? Or rather, are the different processes in the system modeled as open systems or closed systems? So if it's a closed system, then we have one set of equations, right? So our conservation of energy and our second law look a little bit different than if it's an open system, where the first and second law look different. And in these open systems, we'd also have to do conservation of mass. Although that's not even all that difficult in all of the processes except Rankine regeneration, where we're splitting the mass. For all the other open cycles that we did, the mass flow rate is constant throughout the whole cycle. So if we're talking about systems where we're modeling processes as closed systems, there'll be the internal combustion engine cycles, like the diesel cycle we'll do today. Hopefully I'll be able to do it correctly, right? And then the open systems, those are the ones where all these processes are open. Typically, these processes happen in a different component. So the mass has to move from one place to another in order to enter this other process. So all of the Rankine cycles we did, vapor compression, refrigeration, heat pumps, Brayton cycles, jet propulsions, these are all processes where each one of the processes happens in sort of this open system frame of mind. Our last of our three questions is, what's the fluid? So this will come down to, when we get our symbolic solutions, we're actually going to find, wow, that was a terrible sentence. We're going to actually have to find our delta H or our delta U or our delta S terms. And in order to do that, we need to know what the fluid is, right? So we need to know, is it a fluid that's going to go back and forth across a vapor dome, like we'd see in a Rankine cycle or a refrigeration cycle? Or is it something that's going to be where we're going to work with an ideal gas, right? So then we have different sort of choices when we're fixing states with ideal gases, like we'll see in the problem today, right? So we break these things down into things with a vapor dome, Rankine cycles, vapor compression, refrigeration, and heat pumps, or things with ideal gases or air, which is the Otto cycle, the diesel cycle, the Brayton cycle, and jet propulsion. This is always a two-part question, right? If we have a vapor dome, we need to know what the phase is. Is it a subcooled liquid, a two-phase mixture, or some kind of superheated vapor? And if it's an ideal gas, we need to know, is it variable specific heat or is it constant specific heat? So am I actually going to find something like delta H, or am I just going to find Cp times delta T? So that's, I think, how I classify all of these different cycles. I'm happy to entertain any kind of questions about sort of this framework of answering problems, or we can just get to the diesel cycle problem that we're going to try to go through today. Perfect. So I am going to assume that means we're going to try to do this diesel cycle problem. So I am going to try to do this using this writing tablet. So we will see how this goes. Now, Jack, I think that you have a problem for us.
Yeah, I found one in the textbook that looks pretty interesting.
Interesting.
Should I just tell you where it is in the textbook, or should I say the whole problem out?
Yeah, you can read the problem, but I might ask you some things, but I'll try to pick up the information that I can in the state table here.
All right. Consider an air standard diesel cycle. At the beginning of compression, P1 is equal to 14 pound force per inches squared.
Yep.
Temperature 1, 520 Rankine. The mass of the air is given at 0.145 pounds, and the compression ratio is 17. The maximum temperature of the cycle is given at 4,000 Rankines. And you need to find the heat addition in British thermal units, the thermal efficiency, and the cutoff ratio.
Perfect. So now it did say variable specific heat, right? It said an air standard analysis. So we'll go through this as if it was a variable specific heat analysis. I don't know that we'll have time to do all the interpolation, but I'll at least show you how I would go about doing that. Okay? So we know that this is a diesel cycle, right? So because it's a diesel cycle, I'm going to draw a PV diagram. So if I have a choice, if it's a closed system, I'm going to prefer to draw a PV diagram. And if it's an open system, I'm going to prefer to draw a TS diagram. So state 1 to state 2 is this compression, right? So here we're going from state 1 to state 2. What makes a diesel cycle is that we're adding heat at constant pressure. That gets us over to state 3. State 4 is going to be vertically above state 1, if I can do this. Right? We'll pretend that that's vertical, right? Because here our heat rejection is still going to be at constant volume, right? So now I know that I'm adding work to my system from state 1 to state 2, that's compression. From state 3 to state 4, I'm getting work out. From state 4 to state 1, I'm rejecting heat, right? So that's Q. And then what I really would like to do here, right? This is constant pressure heat addition. So I'm adding heat here, but because this is not a vertical line, I also get a little bit of work out here. So this is what a PV diagram for a diesel cycle looks like, right? And the sort of unique thing about this diesel cycle, right? What makes a diesel cycle is that this happens at constant pressure, this heat addition. And that makes our life a little bit harder because we've got this two-stage power stroke. We're getting work out here and we're getting work out here, right? So now if I go into this problem, right, it's asking me to find Q in. So I'll start over here in part A, right? So it wants me to find Q in. So this means I'm going to do conservation of energy, right, or the first law, between state 2 and state 3, right? Because that's where I'm adding heat. I'm adding heat over here. So I do the first law between state 2 and state 3. I see that delta KE plus delta PE plus M times delta U. This is going to be, well, I'll just get rid of the delta here because this is always the end minus the beginning, right? So here this is going to be U. This is U3 minus U2 is equal to Q in plus, no, Q, delta is a Q minus W, right? So this becomes Q minus W. So there's a couple things that I know here. I know that we're going to neglect kinetic energy. We're going to neglect potential energy, right? I also know that this work term is going to be the integral of PdV. So I'm going to now try to isolate for Q in here. So this is going to become Q in is equal to M times U3 minus U2 plus the integral from 2 to 3 of P dV. Right? But I know my pressure is constant, right? So because my pressure is constant, I can bring it out, right, of the integral. So this is going to be M times U3 minus U2 plus the pressure times, now this is just going to be, I'm going to make this here, because this is big volume here, right? I'm going to make this now a little volume, and I'm going to do that by multiplying by mass. So I'm going to say mass times all of this stuff over here. So this is now going to be pressure times, this would be V3, little v3 minus little v2. Now the thing here is I can collect these different pieces of information, these different terms, by their state number. And I recognize that this pressure here So P is equal to P3, but it's also equal to P2. So when I multiply P by V3, I'm going to call it P3. And when I multiply P by V2, I'm going to call it P2. So now my equation becomes mass times U3. Now this is going to be plus P3V3. Right? And now I'm going to make this minus both of these U2, both terms to do with state 2 are negative. So I'm going to bring the negative outside the bracket, and this is going to become U2 plus P2 V2. Right? Now, through the magic of knowing thermodynamics, right, I know that this here, this term is H3, and this term is H2. So Q in is going to be M times H3 minus H2. Now, I can see whether or not I know how to solve this yet, right? So the problem told me what the mass is. Unfortunately, if I go up here and I look at my state table, I don't know any kind of H's, right? So here, I don't know H3, I don't know H2, and I don't know Q. If this was an exam, I would leave this for now because I have this symbolic equation, right? So at least I've demonstrated a little bit that I know how to get an equation here. So I see that Matt's got a question. What's your question, Matt?
Yeah, I was just a bit confused on that part where you said that the H's can be equal to U3 plus P3 times V3.
Yep. So the definition of enthalpy. So enthalpy is just like we made enthalpy up because anytime we fix the state, we know the specific internal energy, the specific volume, and the pressure. So it's a pain if we always have to look those things up. So I don't know if you know this equal sign with 3 different lines in it, right? This is like, it means it's a definition. So the definition of H is that it's the specific internal energy plus the pressure times the specific volume. So this is just the definition of specific enthalpy. So you could leave this like this, but if you did, you'd have to find the specific volume for all these cases. So you could look on something like table 822E, and you could find U3. And then if you knew the pressure, then you could use something like the ideal gas law to find the specific volume. But it's kind of a bit of a waste of your time because once you know the temperature or the reduced volume in this case, you can just find H. And H is U plus PV. So that's,
right.
It just comes from the definition.
Okay, that makes sense, yep.
Okay, so I'm going to leave this now because my general feeling is that if you're not sure what to do, always do the symbolic stuff first. Because if you know the symbolic stuff, then, I think it's the symbolic stuff is pretty consistent from question to question, and sometimes fixing the states is difficult. So I'm just going to leave this, and I'm going to go to part B. Right? So now, if I come over here, then I should get my pen back. Right? So now here for part B, we're asked for the thermal efficiency. Right? So thermal efficiency, we know, is net work divided by Q in. Right? But because the whole cycle is isentropic, it's all ideal, this is also going to be, whoops, I don't know what happened there. This is also going to be Q net over Q in, right? Now Q net is Q in plus Q out, so long as we're using the first law to get both of these terms, right? So Q out is going to be negative. I can divide all this by Q in, and this is going to be equal to 1 plus, I'll write Q out in red because I know it's supposed to be negative. Q out over Q in. Now, there's nothing wrong with leaving it like this and finding all three work terms, right? So here, if we look back up at our PV diagram, there's three different terms for work. And you can find all of those and get W net. But because we've already found heat in, to get heat, the net heat, I only have to find one more term, right? So I think it's a little more efficient, right? Or maybe you could call it laziness if you want. But I like to do as little amount of work as I can to get the right answer, right? So that's why I like to do it this way. So I already know, like when I look at this equation, right? I know Q in. Unfortunately, or at least I have an equation for it, right? I don't have a numerical value for it, but I don't know the efficiency. I don't know Q out. I don't know Q in, but I can get Q out if I look back at my PV diagram, right? So here, Q out happens over here. Heat is leaving as I move from state 4 to state 1. So I want to do the first law from 4 to 1. So here again, I know that delta KE plus delta PE plus M times, now this is U at the end minus U at the beginning, so this is going to be U1 minus U4. Right? Matt, did you have a new question?
Oh, my bad. I forgot to put my
That's
hand
okay.
down.
No big deal. Right, so this is going to be Q out now minus W from 3 to 4. Or sorry, from 4 to 1. But the beauty here is that unlike the heat addition, right, the heat rejection is a simple process, right? Because here, delta V is equal to 0. So when I look at my PV diagram, right, remember work is the area under this line. And if we pretend that I drew this line vertically, right, which is what I was trying to do, there is no area under a vertical line. So that means that the work here from state 4 to state 1 is equal to 0. So if I come back here, this work term is 0, right? And here I get something that maybe I was expecting, right? I get that Q out is equal to the mass times U at the end of the process, U1, minus U at the beginning of the process, U4. Now here, we expect U4 to be bigger than U1, so we expect this term to be less than 0, which makes sense because I know Q in is positive, right? Heat in is positive, so heat out better be negative, otherwise I'm going to get a thermal efficiency that's bigger than 1 or bigger than 100%, and that's not possible, right? So here, if I want my expression for thermal efficiency, then this is going to be 1 plus, here I'm going to have U1 minus U4 divided by, I look back up from my Q in expression, and that since both of these are multiplied by mass, I guess I'll put it in and then I'll cancel it out, but this is going to be H3 minus H2 minus H2, right? And all of this is going to be multiplied by the mass over the mass, and that's just going to cancel out, right? So that's going to go to 1. Right, so now over here, right, if I take stock of what I know here, it's going to look a little bit depressing because I don't know the efficiency, I don't know U1, I don't know U4, I don't know U3, and I don't know U2. So the good news here is that I have an expression. The bad news is I got one equation and I got 5 unknowns. But I guess the other piece of good news is most of the unknowns, if I can fix all my states, I should be able to find the specific internal energies and the enthalpy. So if I can fix all my states, then I'll only have one unknown. So even though this looks a little bit depressing because we're like 0 for 5 in this equation, it's not too bad because if I can fix all my states, then I'll be 4 for 5, which is what I want, because I want one equation and one unknown. Right? So that's part B. Now part C, the cutoff ratio, this one sometimes just falls out, but we'll go through and we'll draw this out. So part C, this is the cutoff ratio. So there's two ratios here that are important in our diesel cycle. So the Otto cycle was a little nicer because there's only one volume ratio. So the volume ratio that matters in both the Otto cycle and the diesel cycle is the compression ratio. All of these volume ratios are always the big volume divided by the little volume. So the compression ratio here for this compression cycle is going to be V1 divided by V2, right? And that was given in the problem. I think is what, 17, I think? Yeah, so this is 17. So that's good. But our cutoff ratio, this is the volume ratio for the heat addition process. Now again, it's going to be the large volume. That's V3. You can always tell the large volume, right? Because volume is on the x-axis. So it's the one further to the right. So the bigger volume here is V3, and the smaller volume is V2. So, working down here to part C, this volume ratio for the cutoff ratio is going to be V3 divided by V2. Now, one of the things that I always say when the process is, where the working fluid is air or an ideal gas, is look for the isentropic processes, because there's some special things we can do, right? So here I might ask myself, so to do this process, I want to know something about this process as I go from state 2 to state 3. So is it isentropic? Unfortunately, the isentropic processes have to be adiabatic, right? We could see that if we were doing the second law analysis here, we would see that for an isentropic process, for delta S to be equal to 0, we need to have Q equal to 0, and that's not the case here. So here, this is no. The isentropic processes in this process, or in this cycle, are the ones where there's only work, right? So it might be good to identify those here when I draw this out, right? So here I can say that this process from 1 to 2, that's isentropic, because there's only work. From 3 to 4, this is also isentropic, right? So, or maybe it's better to say delta S is equal to 0, right? Or delta S is equal to 0, right? Anytime there's heat transfer, it's not isentropic. So I can't use an isentropic relationship. So instead, what I'm left with going between states 2 and 3 will be the ideal gas law. Oops. Right? Now, if you remember the ideal gas law in our class, right, we'll be talking about pounds or kilograms of mass. So we say that pressure times volume is equal to m times the specific gas constant times T. Now the cool thing is that for this cycle, for all of these processes, because we're assuming that there's no, so here it's closed, right? That means that the mass is constant, but we're also going to assume that there's no chemical reaction, right? And that means that R is also constant. So now our ideal gas law, we can look at this and say that P V over T is equal to MR. So this is true if we go P2 V2 over T2, but it's also true if we're talking about state 3, and really any state in between during the process, but we typically know these endpoints or the beginning points of all the processes, right? So this would be P3 V3 over T3. So here, what I actually want up here is V3 divided by V2. So here I can use the ideal gas law, and I can see that V3 divided by V2, right? So that's going to give me here, so I'm going to get P2 over P3 multiplied by, I'm going to get, so here I'd move this T up, so this is going to be T3 over T2. Now the cool thing about this particular process, right? So if I go up, I guess it's the double-edged sword of the diesel cycle, right? So this is the heat addition process. So it's a bit of a downside for us that this happens at constant pressure, because that's what's giving us this work term, and that's what makes diesel cycles harder than Otto cycles. But because this is a horizontal line, right? This is a constant pressure process. That means P3 is equal to P2. So if I go down here back to part C, then I see that this P2 over P3, this is just going to be 1, right? So that means that now I also have this expression here that V3 over V2 is going to be T3 divided by, divided by T2, right? So again, I'm at a point where I have this, right? Remember, this is RC, right? So here I can say RC. I don't know RC, I don't know T3, and I don't know T2. But if I could fix all the states, then I would be able to solve the problem, right? So at this point, I have enough information to get the symbolic solutions for all of the processes, right? Or for all of the parts of this problem. And these are the three things that they're probably going to ask you in any kind of a diesel problem, right? So now it's how do we fix the states, right? And sometimes, this is the hardest part of the problem, right? So how do we fix the states? So when we're trying to fix the states, right? So if I come up here and it's like, right? Like, how do I do this, right? I got two options, right? So here, there's only a couple equations I can use. So I can use the ideal gas law, always. So I can always use the ideal gas law, and sometimes I can use the fact that delta S is equal to 0. Now, if delta S is equal to 0, I can look on my equation sheet, right? So for isentropic processes where we're talking about air, if it was constant specific heat, right, then I could use these equations. But it's not constant specific heat in this So it's not constant specific heat in this problem. It doesn't seem to like if I try to play with those equations. Sorry about that. So it's not constant specific heat, so I can't use any of that stuff, right? So instead, I have to use these isentropic value or these isentropic expressions for air, right? And because I don't really know pressure ratios when I'm talking about diesel cycles, right? And Otto cycles, usually if it's closed systems, I know volume ratios. So here I'm going to use that VR over VR is equal to V over V, right? So the ratio of these reduced volumes is going to be equal to the ratio of the volumes. So here, because it's variable specific heat, then this means that if we have a process that's isentropic, then VR, I'll say 1 over VR2 is going to be equal to VR, or V1, sorry, V1 over V2. This would also be equal to little v1 over little v2. And these should be lowercase v's too. Pretend that's a little lowercase v. Right? So this is the relationship that we're going to use. Right? So we're going to start with state 1 because state 1 is the one that I know the most about. Right? So here from state 1, I know the temperature, 520, the pressure is 14, and I know the mass, right? Right, so here I think if I remember this right, T1 was 520 Rankine, P1 was 14 psi, and there was some mass. Right? Now, from state 1 to state 2, this is an isentropic process. Right? So that means I can use both of these expressions. So I guess first I want to fix state 1 though, right? So from state 1, I'm going to remember this. So where is it? Here, right? So this is what my state table would look like. This is not the right one because it's in Kelvin, but it would look the same. Did I open it here? Oh, here it is. Right, so here I would see, as long as I know T, H, U, PR, or VR, I only need one of those pieces of information, and then I can fix the state. So here, let me try to get a bit of a split screen here. Right, so here we know that the temperature is 520, so I can just read this off. So now, what do I need for state 1? State 1's not on the horizontal line, so now when I do interpolation, I want U1. So U1 is going to be, I'm going to read it off here from 520. This is going to be 88.62. And this is BTU per pound mass, right? And then I can also get VR. VR at 520 is 158.58. This has no units. And I know P1 is 14 psi, right? So now when I move from state 1 to state 2, this is isentropic. So I know that from state 1 to state 2, I know that VR1 over VR2 is going to be equal to V1 over V2, which is the same thing as saying VR2 times the cutoff, or times the compression ratio. So this is going to be 17 times. Oh, but I want VR1, right? So here I would scratch this, right? So this is true, right? But I want to isolate for VR2. So here VR2 is going to be equal to VR1 times V2 over V1, right? Or VR1 divided by 17. So I'll pull up my calculator. So I get 158.58 divided by 17. So this VR2 is going to be 9.33, and that's dimensionless. So now what I'd do is I'd use this to interpolate. So I'd look now, so for a VR, see how these are going down. So it's got to be 9.33. So it's going to be in between 1520 and 1560. So now I'd interpolate to find. Now at state 2 I need H, right? Because that's on the horizontal line. So I'm going to try to find H2. And then I'm also going to find T2. Now I don't know the pressure here. So I'm also going to have to use the ideal gas law. So here I'll use the ideal gas law. And I'll say that P1 V1 over T1 is equal to P2 V2 over T2. Right? So now here, because I've done this interpolation, I now know T1. Well, T1 was given. P1 was given. I don't know V1, but I know V1 over V2. I do know T2, so I can move this over, and I can see here that P2 is going to be equal to P1 multiplied by T2 over T1. Right, so I got T2 from the interpolation here, so I know T2. And then this is also going to be multiplied by V1 over V2, which is the compression ratio. So now I can get P2. Right, so because I'll go through the whole problem. We'll run over time. So if you're welcome to stay if you like. If not, I'll post the video too online. So now we know at state 2, we know the pressure, we know the temperature, we know the specific enthalpy, and we also know VR2. So now what do we want to do? So that was from state 1 to state 2. Now we go from state 2 to state 3. This is here delta, oops, I don't know why that keeps happening. Here delta S is not equal to 0. So all we can use is the ideal gas law. So here we know from before that we have, oops, P2 V2 over T2 is equal to MR, which is equal to P3 V3 over T3. Now, we know that these pressures are the same. So, the other thing that I know is that T3, which is given, right? That's the maximum temperature in the problem. So, T3 over T2 is going to be equal to V3 over V2, right? And this I don't have yet. This is my cutoff ratio. But now, at this point, because here I already found T2 from last problem, and now I've just found T3, or T3 was given, right? Because it's the maximum temperature in the problem. So now I know T3, and because I know T3, right, I can go back to table A22E, and here T3 was 4,000. So it would be better if we had a table that went all the way up to 4,000. So maybe on the version of the textbook that this problem came from, or maybe this this table here is maybe just cut off. So if we had 4,000 on the table, then we would use this. Where are we? Sorry about this. So here, once we knew T3, so state 3 is, again, it's on that horizontal line. So that means we need H3, but we would also find VR3. So the next thing, so now at this point, now we know H3, right? So we found H3, and now we can try to go between state 3 to state 4. Now this process is isentropic. Delta S is equal to 0. So if we go back up, so that we're on page, I don't know, it says 1 of 9 down there. So I'm pretty sure that's incorrect. So here, right, so now if we go from 3 to 4, this is isentropic, right? Because there's only work, there's no heat transfer here. So now, because this is isentropic, we can use the relationship that V4 over V3 is going to be VR4 divided by VR3. Right? So we can also use the ideal gas relationship. We can say that P3V3 over T3 is equal to P4V4 over T4. Now we got a couple issues here, right? We don't know the pressure at state 4. We don't know the temperature at state 4, so this is not really going to help me, at least yet, right? And I also don't know the ratio of V4 divided by V3. Yep. Jack, I see I got a question.
Yeah, I did find it. Well, the further down tables does go up to 4,000 Rankine.
Okay, so this file that I have is probably just cut off too early.
Yeah, it's cut off. It's on the next page.
Okay, cool. Yeah, this is the end of this document, but okay. So that's good. So in the textbook, it goes higher than that. So I got to check
it
that.
goes up to 5,000.
Okay, that's good. So I will check on the materials that are available to you for the exam. I'll double check that you'll be able to fix states if you're asked to do that with variable specific heat. So this part here, we don't know V4 over V3, and this is the part, I don't know if you remember, but this is one of the things that's tricky about this diesel cycle. So here, we're going to do, this is kind of like the sleight of hand that happens in the diesel cycle. So there's a couple things we're going to do here that we're going to remember that V4 is equal to V1. Right? So, because remember this, as we go from state 4 to state 1, that's a constant volume heat rejection. So that's the same. So this is going to be V1 divided by V3, right? That's equal to V4 divided by V3. Now, I'm going to multiply this thing by 1, right? I'm only going to do it on the right-hand side. You could do it on the left-hand side too, but then it's just going to be times 1, so who cares? But it's going to be a special kind of 1. It's going to be the kind of 1 that's V2 over V2. Right? So we're going to not leave it like this. We're going to group these things a little bit differently. So this will be V1 over V2 multiplied by V2 over V3. Right? So V1 over V2, this is our compression ratio. V2 over V3, this is 1 over our cutoff ratio. So this V4 divided by V3 is equal to R over RC. So if I put this back, now I could get VR4 is equal to VR3, which we fixed back here, multiplied by R over RC. So this will give us VR4, and then once we have VR4, we can interpolate on A22E. Oops. I don't know why this is. Oh, because I think I'm pressing the button. So this will give us, so A22E. Here, this is state 4, so we want U4. I can find T4 if I want, but I don't think I need it for my equations. So now once I've done this, right, so now I have U4. Over here I've got H3. From state 2, I got H2. And then here in state 1, I got U1. So now when I go back up to my symbolic solutions, I found T3 and T2. Right? So now this is known. I don't have a numerical value for you because we didn't actually fix the states. But I know these two things now. Right? T3 was actually given from the beginning, so this really should have been a check mark. But we don't have We have state 2. Over here, we found the U's on the vertical line, U1 and U4, and we found the H's on the horizontal line, H3 and H2. So I can use that information to find the thermal efficiency. And then over here, I found H3 and H2. So now I can find the heat transfer that goes into the cycle. So that's enough to get numerical answers for the problem. So ultimately what we did, right? So we looked at the different components of the problem. We solved them all symbolically. And then we went through the effort of fixing all the states. So in a diesel cycle, it's important to know which states or which processes are isentropic, because then you can use the isentropic relationship. Here we talked about variable specific heat, but in this, if we were doing this as constant specific heat, the methodology is essentially the same, just you'll use a different expression when you get to the isentropic relationships, and your delta H's and delta U's will become some kind of specific heat multiplied by delta T. But then the other thing that people mess up with the diesel cycle is this kind of sleight of hand that we did at the end, because you'll get to this thing when you're going between this process and you're like, I have no idea what V4 over V3 is. So you have to remember that there's this kind of magic trick that we can do to make V4 over V3, or sometimes this will be V3 over V4 if you flip it over, right? And that's going to be, if it's V4 over V3, it's going to be the compression ratio divided by the cutoff ratio. But if it's V3 over V4, then that's going to be the cutoff ratio divided by the compression ratio. So that, I think, this is one of the big tricks that people miss in the diesel cycle. So that, and remember that the processes that are isentropic, you have special relationships for. So I know we went a little bit over time, but I'm happy to answer questions if people have them.
Could you go back up a little bit to, I think it was when you're trying to get the for part A. Yeah, I was confused a little bit by the math here of how you spreaded the M to...
Oh, sure. So here, I'll write that out. So because this is PDV, right? Mm-hmm. So I could write this. Here, let's... I'll underline this in blue, and then I'll do the work up here, okay? So P times dV, right? This integral is the same thing as this integral of P times M times d little v, right? It's because V is going to be mass times specific volume. But the mass is constant, so I can pull it out, and then I can pull it out of the integral too.
Mm-hmm. That makes sense, because by multiplying M times that, you get big V.
Yeah.
Okay.
And you wouldn't be able to do that if it wasn't a closed system. So this we can only do because mass is a constant.
Mm-hmm. Okay, thank you.
All right, if there's no other questions... Excellent. And I'm looking forward to doing a turbojet problem next class. Thanks, everyone.